Vibration analysis, signal processing, integration, combining techniques for advanced signal analysis. What is integration in vibration analysis? Integration in vibration analysis is the mathematical process of converting acceleration data into velocity and displacement. This is essential because different machine faults manifest more clearly in different amplitude units. For example, acceleration is sensitive to high-frequency events such as bearing defects, velocity is widely used for general machine condition monitoring, and displacement is preferred for low-speed machinery where large movements occur. Integration can be performed either in analog form before digitizing the signal or digitally after sampling. Understanding integration is critical for analysts because improper application can distort data and lead to incorrect diagnoses. The process involves dividing by frequency during conversion, which can amplify low-frequency components if not properly filtered. Therefore, integration is not just a mathematical step but a diagnostic decision that influences the clarity and reliability of vibration data. Why integration is important, purpose and diagnostic relevance. Integration is used to convert acceleration readings into velocity or displacement because each unit emphasizes different frequency ranges and fault types. Velocity is the most common diagnostic unit because it correlates well with machine severity across a broad frequency range, typically 2 to 2000 Hz. Acceleration is ideal for detecting high-frequency faults such as early-stage bearing or gear defects, while displacement highlights low-frequency motion, making it suitable for slow-speed machines and journal bearings. By integrating data, analysts can tailor their analysis to the specific fault conditions they are investigating. However, integration must be applied carefully, as it can introduce errors if low-frequency components are amplified excessively. This is why high-pass filtering is often combined with integration to suppress unwanted low-frequency noise and prevent distortion in the velocity or displacement spectrum. Integration methods and challenges, analog versus digital integration, low-frequency amplification and filtering. Integration can be performed in two ways, analog integration and digital integration. Analog integration occurs before the signal is digitized, which means the continuous analog signal is processed through an integrator circuit. This approach can amplify low-frequency noise, requiring the use of high-pass filters to prevent distortion. Digital integration, on the other hand, is performed after the signal has been sampled and digitized. While digital integration offers more flexibility and precision, it still requires filtering to avoid issues such as drift and baseline wander. Both methods share the challenge of low-frequency amplification because integration mathematically divides by frequency. As frequency approaches zero, the calculated velocity or displacement approaches infinity, which is unrealistic and problematic. Therefore, proper filtering and understanding of integration principles are essential for accurate vibration analysis. One of the main challenges in integration is the amplification of low-frequency components. When converting acceleration to velocity, the process involves dividing by frequency, which means very low frequencies become disproportionately large. This can lead to misleading results and obscure the true condition of the machine. To address this, high-pass filters are applied during integration to remove low-frequency signals that are not relevant to the analysis. These filters typically have a cutoff around 10 Hz, ensuring that structural movements or slow drift do not dominate the velocity spectrum. High-pass filtering also prevents DC offset and drift, which can distort the waveform and spectrum. Analysts must be aware of these issues and configure their data collectors appropriately to maintain data integrity. When to integrate and when not to integrate, example. Integration is useful when analyzing mid-frequency faults or general machine condition, but it is not always appropriate. For high-frequency faults such as bearing or gear defects, acceleration data should remain unintegrated because integration can diminish the visibility of these critical components. Similarly, when analyzing very low-frequency behavior, such as structural resonance or slow-speed machinery, integration may filter out important information if high-pass filters are applied. Analysts should also consider the diagnostic goal. If the objective is to detect early bearing damage, acceleration is preferred. if the goal is to assess overall machine severity, velocity is ideal. Understanding these nuances ensures that integration enhances rather than compromises diagnostic accuracy. Examples showing the same vibration dataset displayed in acceleration, velocity, and displacement units. In acceleration, the spectrum reveals high-frequency peaks associated with motor rotor bars and bearing components. When integrated to velocity, the spectrum emphasizes mid-frequency components, providing a balanced view of machine severity. Further integration to displacement highlights only low-frequency components, which is useful for slow-speed machinery but hides critical high-frequency details. This example illustrates why analysts must choose the correct unit and understand the impact of integration on the diagnostic process. Key takeaways on integration. Integration is a powerful tool in vibration analysis, enabling conversion between acceleration, velocity, and displacement to suit different diagnostic needs. However, it introduces challenges such as low-frequency amplification and potential data distortion if filters are not applied correctly. Analysts must understand whether integration is performed in analog or digital form, verify the filter settings, and select the appropriate unit for the fault type being investigated. Proper application of integration ensures accurate, reliable vibration analysis and prevents misinterpretation of machine condition.